Hi, I'm Gillian Chang. I'm a computational designer and the fabrication lead at Martin Brothers. And I'm going to talk about what we're doing on our computational team and how we're leveraging parametric modeling to balance the very real practical constraints of construction with the highly custom geometry of our current project. So first off, I just want to say that due to our NDA, I've substituted industry examples or otherwise abstracted elements from our project throughout this presentation. I'm sorry, but I just can't be more specific. So a bit of context, Martin Brothers is a light gauge framing company here in LA, but I actually come from an architecture background. And prior to this, I worked at Gary Tech. And in fact, our entire computational team comes from the architecture side of AEC, but we found our way to this project via a range of different industries, automotive, furniture, robotics, manufacturing, stoneworking, fine art, you name it. And we definitely think of ourselves as designers. So traditionally, the architect is conceived of as this master builder who controls every last detail, but now the different roles are often partitioned out. The design architect separate from the executive architect, engineer of record, GC, etc. So as design build subcontractors, we are absolutely making design decisions on how best to realize our scope. And because we ultimately are responsible for seeing it through construction, we have to inform our design with construction constraints. Combining this with automation has enabled us to scale our efforts, bringing tools that we originally learned on the design side of architecture and applying them to fabrication and installation. So where computational strategies are often most useful in architecture is on projects of either very high geometric complexity or very large scale, or both. You get the biggest payoff when you can automate something that is very time consuming in terms of difficulty or in terms of quantity. And our facade project is both. Our scope is a light gauge facade substructure spanning from primary structure out to the complexly curved skin. It's well over 1,000 individual facade panels that are each uniquely supported. Automation buys us valuable time to design and solve the complex problems and replicate those solutions at scale. So building this project is a more difficult challenge than straightforward mass customization. It's actually easy to design it to be 1,000 different pieces, but it's hard to design one piece that works in 1,000 different ways. So we're striking a delicate balance between the variation that's required by the geometry and time and money to build it. So how do we do this? It starts from the design. I'm taking an example from one part of our system to showcase how the design has evolved to be more friendly to mass production, even over the course of this project. A lot of credit obviously goes to our engineers for evolving the system from the first design you see on the left, which is almost like waffling the facade, to a more strategic system, arranging more standard things in very specific ways to achieve the exact same geometric variability. It's an easy solution to simply waffle a complex surface to rationalize its substructure, but it's actually much harder to build. So here, each gray member represents a piece that has to be cut to a specific size, laid out specifically, assembled, and each red dot represents a connection that has to be made manually by our team. So the mini trusses you can see follow very closely the curvature of the facade and have a lot more connections. It's a lot more cutting. It's a lot slower to build. The later design, which has fewer connections and more standard parts, isolates the horizontal variability to the main beam and the vertical variability to these threaded rods. It's a more rationalized and more elegant solution. And now that we have all these standardized parts, thanks to the scale of the project, we can figure out how to further reduce labor by marginally increasing material waste. We're optimizing stock parts, grouping those threaded rods I showed into a few standard lengths to eliminate time spent measuring and cutting for each panel. So this is just one example. We're actually doing the same sort of calculation across our whole system. We're achieving mass customization more cost effectively by strategically concentrating the variability in certain components, which are then custom laser cut or milled. This allows the rest of the components to be very standard stock commodity elements. And the consistency afforded by this system makes each frame much, much simpler to assemble, because at the end of the day, our field team, a human, has to build this with their hands. A measuring tape, laser level, chalk line, that's pretty much it. As an added bonus, the consistency also allows us to fully automate fabrication and assembly drawings. In order to do this at scale across the project, we write scripts early and often as a design tool. Thinking about the design systematically and seeing it play out across all the different geometric conditions reveals inherent assumptions and breaking points in the design. A 2D detail might make sense in an idealized, typical 90-degree section, but only by proliferating it in 3D across the project do we realize, hey, this design actually hits a geometrical or constructability limit at a certain point. How often does it hit that limit? Do we need to change the entire detail, or can we create variants that we can swap in and out? This then goes back and informs the design in a cycle of development. It's where we meet engineers on one side and framers on the other and bring them together. Having gone through that effort of development, the 3D model is really real for us, and it drives everything in the process. It drives coordination, a combination of 2D and 3D extractions for approvals, dimensional control, fabrication, QA/QC, scaffolding, installation, everything. This represents a shift in the point that decisions can be made in the process. So while traditionally you would be sure not to over-constrain a drawing to allow space for the builders to react to hit those critical dimensions, on this project, the irregular geometry, tight tolerances, and delicately balanced coordination with other systems means a much higher degree of control is necessary from the design side, and a much more deterministic process as a result. So how then do you react to unexpected problems on the build, out of tolerance elements? We are employing a few different approaches. First, you can design in increased tolerance in the system, allowing for a controlled space to respond and compensate for those issues. We are employing adjustable joints, which are critical at the interface between systems, the baton pass of tolerance, if you will. Another way you can deal with this is to give your field teams access to the 3D model, giving them the context they need to make decisions in the field. Our framers are asking to see the digital model, and they're starting to use model technology, which is super exciting. And we're actually partnering with our sister company to use the HoloLens 2 on site, equipping the field team with a model in a more intuitive way. So between these two responsive strategies, tracking the deviations in the build becomes its own set of parametric inputs, informing our installation and as-built modeling. And finally, perhaps most idealistically, we can integrate the process from beginning to end, ensuring that every party along the way is highly precise and hits their own narrow targets. The 3D model is really pushing the industry forward, and everyone is being asked to step up. We actually need tighter tolerances than a lot of our suppliers are used to. So we work very closely with them to build jigs, establish new QC protocols to enable them to hit those very tight tolerances. We also coordinate very closely with all the other parties involved to give them the space they need if they need additional space. So in keeping with this year's conference theme, I wanted to highlight some areas of overlap we found with other industries on this project. Firstly, building this project is a major logistical challenge. Trying to minimize the 8 deadly wastes of the Toyota method is an ever-present challenge for our procurement team, our builders, project management, but also the computational design team. The threaded rods example reduces excess motion and overprocessing, for example. But in order to even get to that point where we can optimize and do quantity takeoffs, the model has to be fabrication ready. So the concerns of just-in-time manufacturing actually go beyond that to drive also just-in-time design development. We're also using technology from the aerospace industry on our quality assurance and quality control team, who verifies that what is built falls within agreed upon tolerances. QA/QC in aerospace is a hard stop check, where tolerances are incredibly tight and accuracy is critical because even a tiny error could be life-threatening. So the laser tracker we're using is accurate to 75 microns. And our QA/QC team is working directly with metrology experts, the developers of scanning software, and best fit algorithms to adapt this hyper-accurate system for the construction industry. We're using it to validate not only individual parts, but also assemblies and the final install. So once all those parts that we disaggregated into the stock and custom parts for optimization and procurement, once all those parts are re-aggregated into the support frame substructure, we scan that assembly to ensure its accuracy. And then once it's attached to the actual panel, the whole thing is scanned again. And the results from this inform the settings for those adjustable blind joints. And then once the panel is installed and hanging, it's scanned once more to confirm the installation that it's sitting exactly the way we intended. So the speed of this technology in linking model and built assembly allows our QA/QC team to quickly provide feedback to our builders for fine-tune adjustments along this whole process. And we absolutely predict increased accuracy in building construction in the future, especially as mass customization and automation becomes more affordable and enables us to hit tighter tolerances all around.
10 minutes left.
Okay. Installation is another area of industry overlap, this time with manufacturing more broadly. Our study assessing if the final install position for each panel can be reached with our equipment directly parallels the ergonomic studies for an assembly line, which ensures that workers can safely perform any given task. For us, our forklift weighs 50,000 pounds, and on a complex site with other trades working at the same time, it's not like you can just drive it anywhere. We have to make sure that given where the forklift has to be positioned, the panels that we need are all within reach based on each panel and its substructure's weight. Similarly, assembly lines are carefully studied to confirm that any given process falls within the, say, 5th to 95th percentile of human arm length and range of motion. These are hard constraints, and the clashes are real. When something falls outside of this range, we start having to design custom tools, a special wrench to reach into tight corners, or for us, custom clamps on the ends of the forklift. This can add time to switch between the tools and obviously expense to make them. But it could be the best choice if we're designed into a corner. And then once we've designed that custom tool, we then perform the exact same study, ergonomic study, with a new tool to see how it can be used, if it can cannibalize from other standard tools, etc. I think the building industry also has a lot to learn from industrial and automotive design in terms of rigorously controlling curvature. A favorite example of mine is the squircle, which Apple uses instead of a rounded rectangle. Apple has made the calculation to use this more beautiful gradual curve for the sake of the design, and it makes sense for them as a premium product. And with the aluminum unibody construction, it's not like it actually costs them more to achieve. But deciding between these two should be a conscious, calculated choice. We need to think long and hard which makes sense where on any project with complex curvature. This is a well-established part of automotive design. Surfacing is a crucial step between the conceptual design and execution, which I think is often overlooked in architecture, with the result of much more difficult and costly construction in the end. Good automotive surfacing is handcrafted and artisanal, making decisions informed by the engineering criteria, and yet has the agency to translate the ideal, perfect design geometry into more rational, technically achievable geometry without sacrificing that original design intent. It's well worth investing this time and effort upfront, because minute changes that are ultimately imperceptible could really save a ton of money down the road. It goes back to the deadly waste of overprocessing. Why make a beautiful and difficult transition with curvature continuity where you're never actually going to see it? Surfacing also gives us the opportunity to find moments of internal repetition and localized symmetries, which allows you to solve the design once, and then you get to reuse it. You get more bang for your design buck. Obviously, a car is symmetrical. The spokes on the rims are arrayed radially, but even if you can't find exact duplicates in the A surface, you can still find opportunities for repetition in the substructure. in an automotive facelift, you keep certain major components and apertures the same, but you're free to change everything else in between, creating the appearance of variability while being able to reuse much of the design and engineering of the B side. For example, the Tesla Model Y and Model 3 were built on the exact same chassis. Really, this is the exact same argument as those mini trusses I showed before versus those beams of the threaded rods. It's arguing for isolating the variation as much as possible to create more standardization. One philosophy that I think ties all of these lessons together is Gunpei Yokoi's idea of taking well-seasoned, not at all cutting-edge technologies and applying them in new and clever, cost-effective ways, which drove many of Nintendo's early successes. For example, the Game Boy issued more advanced technologies which were available at the time, such as higher resolution, a full-color screen, in favor of longer battery life and cheaper price points. Similarly, scripting and detailed modeling and architecture is nothing new, but having an in-house team developing the models and having that directly inform production and installation is absolutely something new for Martin Brothers. And it's really exciting to witness and be part of this broader movement in the construction industry. There's a lot we can still learn from within AEC as well as other fields. And I'd argue that we need to borrow liberally to take what's thoroughly figured out and well established elsewhere and bring it back and apply it to AEC. With the goal and hopefully the end result in the end of better, cheaper, faster, and more beautiful buildings. And that's it. That's all I have.
Awesome. All right, so Jonathan Cortez is going to come up with and help with Q&A.
Oh, thank you so much, Gillian. That was an awesome presentation, to be honest.
Thanks.
Very cool. Yeah, if anyone has any particular questions, feel free to throw them into the chat or into the Q&A. We'll run through and answer them. But I guess until anyone starts sparking up questions, I do have one to start from, which you kind of just ended on. And it's the idea of AEC seems to be an industry that's constantly evolving, right? But you mentioned looking outside at other industries to see what we can learn from them to push forward. We've done that in the past. We learned a lot from car industries and how to build buildings today, but I feel like there's been a bit of a disconnect within the last, like, say, 20 years or so, where we kind of stopped looking outside, and it's been sort of a slower process. What do you think about that?
Yeah, definitely. I think one of the great things about being on this team is seeing people bring expertise back to architecture. So a lot of these are lessons that I've learned from people, from my coworkers who are coming back to architecture or construct AEC from automotive industries and arguing for things like the surfacing example I used, and to rationalize and more carefully consider our A surface before moving into construction, and all of the experience they have building things in robotics and applying that to what we're doing in our project as well. So yeah, definitely for more more lessons learned. Yeah.
Yeah, 100%. I guess to keep on that, also regarding the particular project you were talking about, is there anything you, or actually Martin Bros in general, has learned from this project that can be applied? Because it is a very custom project, but what's interesting is what you take from it that can be sort of standardized, anything that can go further.
Yeah, I mean, I think there's a lot of tools that obviously right out of the box we could reuse on other projects, and if not, components and custom things that we've built that you know, similarly to what Ilke was saying, that you can always reuse those aspects of those scripts on other projects. It's a very similar tasks, like I think even what Core Studio you guys were doing, linking SAP models to your Tekla models. Similarly, we do that with our geometry, linking SAP and our Rhino geometry, for example.
Ooh, we got two questions. We got a question from Charles Portelli, and he says, it was an interesting presentation. There are always analogies being made between AEC and other industries, such as automotive and aerospace. Those industries have economies of scale, which isn't always the case in AEC. How do you deal with the concepts of mass customization?
Yeah, it's a tricky thing because architecture, the capital A architecture, especially like this project, is always like a one-off, right? So that's why I'm arguing for, even within a project, finding moments where you can optimize or get more bang for your design buck by first of all scripting a lot of things, but also finding moments where you can reuse the exact same strategy or exact same design. So yeah, we don't get to exactly repeat the same structure exactly, but by keeping things very consistent and having a very well thought out system that allows our builders to be super familiar with it and know how to react. I think that's where we're finding economies of scale. It is also a large project, so that helps us in terms of being able to bulk procure and produce some things. Yeah.
Definitely. Okay, here's another one from Abhishek. I'm gonna screw up your name, Baviskar. He says, great presentation. I'm curious to know if and how you tag individual parts with some identifier like a barcode or a QR code to make it easy for field crew to look up properties or quickly order replacement parts if they're damaged on site, for example.
Yeah, we don't have QR codes. That's always the dream, I guess, for everything to be tagged. But we do have unique identifiers that are often labeled like stickers on individual parts. So if something, we have had instances of something getting damaged in shipping, or somebody drops a panel, and so we are able to quickly look up and reorder parts and see if we can cannibalize from a different thing that we already have in stock, and address any issues that come up that way.
Cool. Yeah. Another one from Martin Henriksen. He says, do you experience a disconnect between the computational design done by the designers involved in the early stages of a project and the computational design you do later in the production stage? And really great presentation, by the way.
Thanks. Yeah, I definitely feel that disconnect, and I do more in like not being able to be involved earlier, and that's kind of what I'm arguing for with the surfacing argument, is that that I think the disconnect between the design architect and the executive, and then having it be a design build, so ultimately we are also designing some parts, that means that the A surface is the design surface is locked. It's a contract document, right? We can't touch it, which I think makes the project much more expensive, unnecessarily expensive, and difficult to build. I mean, it's a fun problem. Don't get me wrong. I'm enjoying it, but it didn't have to be this difficult, I think. And so I think if there was more involvement earlier in bringing surfacing experts and even simple things like kind of what Ilke was showing with the sizes of panels, and bringing considerations of weight and installation, all of that earlier in the process, instead of freezing it in place as a contract document that can't be touched. I think that would really benefit the project, or any project.
One more from Jonathan Rodriguez, who's ironically, his name is very similar to mine. He says, great presentation. Do you feel the industry wants to move towards what IKEA has done, aka standard parts assembly instructions, or does it become too much at that point?
I think there is definitely that movement. I think also Revit kind of argues for that in a sense, like everything being a little bit more blocks rather than super custom. And I think actually it touches on some of the tools and technologies we've saw earlier today. Definitely, there are sectors, I think, within the industry that could absolutely benefit from kit of parts type, things that's already figured out. But I guess this project and kind of the workflow I'm thinking of is much more for that capital A, super designed type architecture, especially coming from Gary Tech, where that's the market, I guess.
True, very true. Okay, I saw 2 more questions that I did not see there on the chat. One from Rob Otani. And he says, how do you see contractors and fabricators having a seat at the table during design? So I guess, how do you see them collaborating at once?
Yeah, so just for this project, since it's design build, we still have to submit DD sets and all that, drawings and everything. And it is a design, and we do get feedback on the design and revise it accordingly, and it follows very closely, actually, what you would be used to from architecture, I guess. And I guess, yeah, the design of our substructure is, I don't know, it qualifies as design. I don't know what to say. It's I think it could inform the subdivision, I guess, and the surfacing a little bit more. But also, if certain engineering constraints, like just a basic, even just basic offsets from design surface, if that could inform primary structure, that would also eliminate a lot of spots where we find ourselves designed into a corner, essentially, where there's no space to operate in. I think in those ways, they kind of need to, I think subcontractors need that seat at the table.
I guess in a way you're saying, we could learn about the geometry more so, inherit information from a particular geometrical object and see how that can influence other decisions, between everyone.
Yeah, totally.
Not just impose something on the object.
Yeah, it's not, it shouldn't be so disconnected as just this crazy skin and then a box in the middle that's your substructure, or your primary structure. It should be more informed.
Gotcha. Okay, so got 2 more. One from Shannon McMullen. She says, you briefly mentioned your team used Toyota's 8 wastes of lean. Is it common within fabricators or other companies to use this project management process, or did you guys just adopt your own process?
I think they're just common concerns. It's not like we adhere very rigorously to that, but I think they're well-known things. We're always trying to reduce the excess material, overstocking. Transportation is a huge concern, obviously, and storage of material, and defects obviously are a huge concern. So kind of trying to iron out that process while making sure that it never creates idling time in the workflow. We had a big concern earlier during COVID. Well, I mean, it's ongoing, but earlier when we were shut down initially at the beginning, we were really worried because we had all these great guys who were trained up and knew the system super well, and we wanted to keep feeding them information, but we had to stop shipping some of our frames and stuff. So it's definitely a concern. So how we can keep, and it's not like we are stopping the design side of it, so we're still pushing the design side forward, trying to get some things approved and provide information so that people can keep building without building up too much backlog. And it's a big juggling act, for sure.
Yeah, I'm sure with this project it's quite something. Okay, so one more from Mark Pollock, and he said, really nice presentation. I think it ties in really well with the previous one, in that we need to find ways to have our design tools which do what we need them to do really well, and your tools which do what you need them to do really well. we need to create design collaboration and partnerships that allow the seamless flow of info between us to get most out of each project. Is this more of a comment or anyway, topic?
Yeah, yeah, I think working really closely with our engineers and fabricators has been super fruitful. And having that workflow, be in constant communication with the models and sending things back and forth has been like really key in the success of this project.
Cool. I think we're hitting time right now, so I appreciate everyone for sending in all their questions, and a big thank you to Gillian for the presentation and answering everything in detail about a project that no one can really talk about. Me being one of the people who's worked on it. So, anyway, thank you so much. And thanks to everybody else.
Thank you.